Viewers like you make this program possible. Support your local PBS station.
February 18th, 2021. Perseverance, NASA's newest rover, one of the most sophisticated planetary probes ever built, is approaching Mars on an epic quest to hunt for life beyond Earth.
We are under a minute from cruise stage separation.
130 million miles away, a team of researchers anxiously waits
Heading alignment.
as Perseverance attempts to land where no rover has dared land before. Inside a crater that might be filled with ancient Martian life, but is definitely filled with cliffs and sand traps where a rover can crash or get stuck for good.
We're heading toward the ground at race car speeds, so there's no way we're going to joystick this down.
For the first time in the history of Mars exploration, a rover is equipped with the intelligence to try to steer itself out of danger.
There's a very specific timeline of events that have to happen at the correct time for the entire process to succeed.
Navigation.
Perseverance signals its progress
Skycam maneuver has started.
as the team monitors every step. If the rover manages to land in one piece, for about 2 years, it will drill into Martian rock that could hold evidence of ancient life, then collect samples and store them.
For the first time, we are going to collect rock samples and bring them back to Earth.
In the future, another rover will retrieve the samples Perseverance collects. And through a series of daring missions that sound more science fiction than science fact, the samples will be brought to Earth, where researchers can examine them in far greater detail.
We have this amazing technology that can really get those samples, bring them back to Earth, and then do all the really cool analysis that we want to do here on Earth.
This is a very, very large undertaking involving thousands and thousands of people from all over the world.
Thousands of researchers with one shared goal: looking for life on Mars, right now on Nova. Did life ever exist on Mars? And if it did, what would that mean for us?
How special is life on Earth? Why do we not see it on Mars today? Did it ever evolve on Mars? What does it take to get life to evolve on a planet?
That question about life is the one that really perplexes and I think really drives us. Something about our desire to not be alone keeps pushing us forward in the search for life.
I like to call it CSI Mars, right? You know, it's literally this investigation where you're finding all these little clues to put together your story.
The tale of our celestial neighbor, Mars. The red planet. It captures the imagination. Thousands of images paint a picture of a barren, alien world. At the same time, there's something about Mars that's strangely familiar.
I was born on the Navajo Nation. It's a high desert area that actually has rolling desert hills, canyons and rock formations and mountains, and all of that looks like the Martian landscape.
When I look at the pictures of Mars, I see the Mojave Desert, right? Without the cactus, but I can't tell the difference if this image is from the Mojave Desert or if this is from Mars. To me, it makes me want to know more. It makes me want to know, what happened to Mars, or was there life there?
Can the Perseverance rover finally answer this question? We've been searching for the remnants of life on the red planet for decades. From the Mariner orbiters to the successful landings of Viking 1 and 2. Through the twin rovers, Spirit and Opportunity, that crisscrossed the planet.
We've been building our knowledge of the Martian environment through so many decades and so many achievements from so many engineers before us.
But it was the discoveries of the most cunning robotic detective to ever explore Mars, a rover named Curiosity, that set the stage for the Perseverance mission. September 14th, 2012, 40 days after Curiosity landed on Mars, it stumbled upon the unexpected.
I remember the moment those images came down. We were all at the Jet Propulsion Laboratory at the time, and we were all huddled around a giant computer screen, and we were just gazing at this in astonishment because it's not what we had expected.
We came across a whole bunch of cobbles. And when we saw that, everybody's jaw just dropped. Oh my gosh, look at this. This is perfect. It is the classic example of a river deposit. Each one of those rocks, they had to get bounced around in some type of environment that was going to turn them from something that was chunky and sharp and angular to something that was rounded. Rivers do that. Rivers on Earth do that very well. And so when we saw this, it was our first evidence of a river.
Evidence that water once flowed on the surface of the red planet. On Earth, all life needs water to thrive. From the giant blue whale to tiny microbes.
The scientists on the team have discovered all these telltale signatures in the rocks that there were rivers and ancient lakes that existed for hundreds of thousands, if not millions of years.
You can think of Mars as, back in time, of course, as being Earth's slightly smaller, slightly colder sister.
Between 3.9 and 3.5 billion years ago, we think that Mars was a warmer and wetter place. And what's interesting about that is that's the same sort of time interval that life got going on Earth.
We have two planets with similar environments at similar times. One of them on Earth is inhabited. Why wouldn't we expect that the one on Mars would be inhabited?
Curiosity found evidence of a once wet world. But here on Earth, for life to thrive, it needs more than water. It needs nutrients.
We tend to simplify that search for what type of nutrients as what we call schnapps.
When people say schnapps, what they're saying is carbon,
hydrogen,
nitrogen,
oxygen,
phosphorus,
sulfur. And we spell all those, the first letter of all of those out, it's called schnapps.
These 6 elements make up roughly 99% of the mass of the human body. In fact, they make up about 99% of the mass of all living things. If life, as we know it, ever existed on Mars, finding schnapps was key. Could Curiosity, a laboratory on wheels, find schnapps? The rover scooped up samples of Martian soil to decode its chemical composition.
What we found was a diverse chemistry that included carbon, hydrogen, some nitrogen, oxygen, and sulfur, and eventually we found some phosphorus. There's plenty of chemical energy available for life if it had ever lived there.
That's really been the big discovery of the Curiosity rover mission.
Curiosity found the ingredients necessary for life to emerge, but not life itself.
Curiosity has not, in fact, detected evidence for life because it does not have the instruments designed for that purpose.
Perseverance is designed to take the next step in Mars exploration as it ventures into unexplored territory to search for samples of Martian rock in Jezero Crater.
If you want to set yourself up for success for finding ancient life, that is the place to go.
This orbital image reveals what makes Jezero Crater so intriguing.
The key thing that led us to Jezero was this beautiful delta, beautifully visible from orbit. We think that delta must be somewhere around 3 billion years old or older. This delta sits at the end of a beautifully expressed sinuous river channel that came in from the northwest, flowing into the crater rim and filling up Jezero Crater with a lake.
On Earth, deltas form where a river and a larger body of water meet. Sediment, brought in from the river, drifts to the bottom.
The sediments that the river carries they really just fall out and they settle down.
And creates a mud layer at the bottom. Year after year after year after year, it creates these.
Take some of that earthly delta mud, put it under a microscope, and you'll find it's teeming with life. Tiny microbes, among the most ancient forms of life on Earth, arising billions of years before the dinosaurs, and far more resilient.
If we think about Mars billions of years ago, we cannot hope for any large-scale fossils. We can't really hope for fossil bones. We can't hope for petrified wood. We can't hope for fossilized leaves, because none of that life existed even on Earth before maybe 500 million years ago. The only life that we can hope for on this old ancient Mars is microbial. Now, this is where it gets tricky because microbes are tiny. That's what their name says. They're microscopic. And we can't really take microscopes to Mars, but what we can look for are rocks that can be shaped by microbial processes.
And that's what the team hopes Perseverance will find. Fossilized microbes buried in the ancient rocks of Jezero Crater.
This is the kind of thing that is... There were a lot of very interesting debates among the members of the science team trying to figure out which rocks should we sample. What should we be looking for? And we have one example, only one example, and that's Earth.
So the Perseverance science team set out to study the clues Earth has to offer in rocks about the same age as the ones they will search for in Jezero Crater.
We went to this location in Western Australia where the oldest evidence of life occurs, just so we could see what it actually looks like.
There are ripples around the side of the Titanic.
The strange rippled layers of these rocks, known as stromatolites, are actually the remnants of a form of ancient microbial life.
In a stromatolite, you'll see there's lots of convolutions. They're bumpy and lumpy.
Bumps and lumps of fossilized microbes.
A fossilized community of organisms all packaged together.
There are just a few colonies of living stromatolites left on Earth. They look like rocks, but just beneath the surface are layers of bacteria.
These often form in shallow water environments where the microbes sort of have something to live on, and they pile up in these layers, one on top of the other, a layer of gooey microbes, bacterial cells that have this sort of mucousy, gooey substance. And that gooey substance traps sediment, mud or sand that flows on top of it, and then they grow on top of that again, and that process repeats.
So this tells you very specific.
By studying these ancient stromatolites, the team hopes to gain a deeper understanding of what to hunt for on Mars.
When we went out and looked at these rocks, I was very surprised how obvious it was that the structures that we were looking at were, first of all, very unusual and very likely to be biogenic, produced by life. This is a kind of a feature that we could see in Jezero Crater with the cameras that we are carrying with us on the Perseverance rover.
This rover has a ton of cameras. We are carrying 23 cameras. Color cameras, zoom cameras, black and white cameras, you name it, right? Cameras that can see up to like the size of a grain of salt. And so they're all over the place on the rover, right? On the front, on the back, on the top, on the arm. We have two in the robotic arm that are awesome. One of them is Pixel, and the other one, which I love the name, is Sherlock and Watson. You can guess from the name of Sherlock and Watson that the whole point of those instruments is to investigate, right? What is the chemical composition of that target?
We don't have geologists who can bang their hammers on the rocks or take their lenses, or maybe there's even, you can drop some vinegar to see what minerals are present. We can't do that. But we do have a lot of instruments that tell us what is in those rocks.
Perseverance will also be on the lookout for another ancient rock in Jezero Crater. One that is as elusive as it is appealing.
This is a piece of what we would call black chert. Chert is such a fine-grained rock. If you look really close, you can see some sort of blotchy black stuff in the interior of this gray rock. And that black stuff, that blotchy black stuff, is actual fossilized bacterial cells. This is a type of rock that we would absolutely love to encounter on Mars. The tough part is that chert is very, very, very hard to drill. So it'll be a tough decision. If we see a rock like this, we would probably be willing to give up an entire drill bit. The payoff is potentially so huge because we could, maybe bring back fossil Martian cells.
Even if Perseverance finds rocks that look promising, it's not equipped to verify ancient microbes. For that, the Martian rock would need to be studied back on Earth.
Collecting samples on Mars and bringing them back to Earth is one of the most complex things we've tried to do with one of our robots. This is a sample tube, and onboard Perseverance are over 40 of these. And the goal is to fill each one of them with a sample of Mars rock.
A sample tube is loaded inside a drill at the end of the rover's arm.
We had to come up with an entirely unique design to drill into a lot of different rocks and be able to extract core samples that aren't broken into too many pieces. It hasn't turned into powder. So it's actually a very sophisticated mechanism. After we're done drilling the depth that we want to, we do one final motion to extract the core from the inside of the rock.
Now the sample tube, filled with Martian rock, is brought back on board the rover.
We take the robotic arm with Martian sample inside of it, and we dock it inside the belly of the rover.
Where we have another small robotic arm that extracts the tube and takes it through a series of stations.
We want to inspect it. We want to figure out how much volume we may have collected, take some pictures of it, and then we seal that tube, and then go put it back into our storage rack.
So all of that gets done internal to the belly of the rover with a little arm that is moving it around, which is insane.
It took 7 years to design, test, and build this one-of-a-kind sampling system.
We've put a lot into this rover, and we are very invested in it working when it gets to Mars. And so we kind of wait with bated breath, and we do the best we can, and we do tons and tons of testing, and we hope that it is enough.
Inside this massive clean room at JPL, the sampling system, along with 7 science instruments, are carefully loaded inside the SUV-sized rover. Throughout this process, the spacecraft must be kept impeccably clean, down to the micro.
We don't want to send an expensive vehicle like Perseverance to Mars and then just detect ourselves because we didn't work to make sure that we kept the spacecraft and the instruments and everything that it touches as clean as possible.
You want to have a nice, pristine sample without any Earth contamination. So that's why we work really hard to keep that spacecraft clean.
Mujige Cooper is responsible for hunting down earthly microbes that could hitch a ride to Mars on the spacecraft, especially the hardy ones.
The microbes that we're talking about are so resilient, they could possibly survive all of the radiation in space, UV, the temperature swings, journeying to Mars and possibly back. So we have to sample the hardware over time, and we use either swabs or wipes to collect samples, lift them off of the surface, and we bring it to our lab and we put them in these petri dishes. We have to give them food so that the colonies grow large enough so that we can see them and know that they're present on our petri dish.
If some hardy microbes flourish, the surface is cleaned with isopropyl alcohol.
Over the course of the mission, we've taken 16,681 wipes, swabs, and air samples of the spacecraft and the surrounding environment. Pretty good job.
But there's one part of the rover that needs to be as clean as humanly possible. The sample tubes that will store Martian rock.
We had to have an environment in which to put them together and to handle them and to work with them and assemble them. We built an entirely new clean room. The cleanest environments we've ever had at JPL. We take a normal clean room and we start breaking everything down to understand additional sources of contamination and how do we make that room even cleaner. The gloves that they use, how many layers of gloves that they have, how often they need to change gloves, how often they have to change the gowns, when we can reuse things, even the computers that are used in there. We can't bring cell phones into that room. We can't bring everyday objects that you normally associate with how you do your job into an environment that is that sterile and that clean. The sample tube itself looks very similar to a test tube, but that really belies the complexity of the design and the features that are built into the sample tube to help prevent contamination. The gold coating is a mixture of titanium and nitrogen, especially engineered in order to prevent organic compounds from sticking to the surface. And that's on the outside of the sample tube and also inside the sample tube. These sample tubes are the cleanest things that we've ever sent to another planet by far. In fact, these sample tubes were probably the cleanest thing on Earth.
March 2020. The COVID-19 pandemic triggers shutdowns across the country, including at NASA's Jet Propulsion Laboratory. Life as we know it comes to a grinding halt.
It's hard enough to build spacecraft, but on top of that, as we were approaching launch, the COVID-19 pandemic was surging in parallel.
Time is of the essence. It's just 4 months before launch. A limited number of essential workers are permitted on site.
It's very difficult to control whether or not face masks are worn outside of the workplace environment. It's easy when you're in a clean room, that's what you do. You wear your face masks, you wear your bunny suit. We actually felt safer in the clean room than we did in the regular environment.
Despite the team's best efforts, it's unclear whether they'll be ready to launch on time.
We launch to Mars typically every 2 years. And if we miss that opportunity, that's a long time to wait.
One thing to understand about sending something to Mars is that we have a very short launch window. Mars takes about 2 Earth years to orbit the sun, and every 2 years, Mars and the Earth are close enough to each other, and that's when we launch missions between the 2 planets. And if we miss this launch window for any reason, we would have to wait 2 years until we could try again.
And that wait could cost $500 million.
The team recognized we are already on the rails, right? We're about to take off. Let's just get the job done. If we focus on this target, maybe it will unite the whole team as well. And in a way also give hope to everybody, not only on the US, but also around the world, that we still can manage to focus on a mission and focus on a bigger objective and then pull it off.
For me, the bright spot of COVID was actually seeing the team that we had pull together and actually get it done. It's kind of miraculous that we got to the launch pad.
Before Perseverance is launched, members of the team install this plaque to honor healthcare workers.
It's a constant reminder that there are people, making sacrifices to make sure everybody is safe and healthy.
From America's shore to Jezero Crater on Mars, we'll begin with the launch of this Atlas V rocket.
The day has finally arrived. Perseverance is on the launch pad. On a nearby beach, team member Elio Murillo, along with friends and his mom, have come to watch the launch.
This is my first mission, and I'm about to see it take off to Mars. I can't describe how excited and scared and nervous I am at the same time. I'm really proud to be part of this team. And despite the pandemic, we have persevered through this together.
Meanwhile,
Grab my security blanket. Let's see if she'll let me.
other team members like Ian Clark, along with his dog Pixel, nervously watch the launch from home.
Launch director, LD is go, and you have permission to launch.
The bouncing of my leg is accelerating as we're getting closer.
That's good to hear, Joshua, right there.
28 seconds to launch.
8, 7, 6, 5, 4. Engine ignition, 2.
0.
Release and liftoff.
A little bit speechless with what just happened. It's surreal. I don't know what else to say other than I still can't believe that I just saw that.
It's pretty magical. It's what we get to do.
I'm terrified and really excited, but it's scary.
Perseverance is on its 7-month journey to Mars. But for Elio Murillo, the hardest work has just begun.
We're working around the clock. Tonight, for example, I have to go in at 7 and I won't leave probably till 4 in the morning. And that's kind of the nature of the work to make sure we prepare for our landing on the Red Planet. We are working with the Earth version of Perseverance, which we've called Optimism. The rover and the computer that it has on board is exactly the same as the one that's on Perseverance. My job is literally the one they portray in The Martian.
Is this the replica?
This is her.
Okay, let's see it.
Where there's a lab that has the Earth versions of all the vehicles.
Pathfinder.
I work in the real lab that has the Earth version of all the vehicles that have gone to Mars.
It's called the Mars Yard. Here, Optimism, Perseverance's twin, faces some of the same challenges Perseverance will face on Mars.
Only real way to do that is through simulation. So the Mars Yard is where we actually perform driving. We have soil that kind of looks like Martian sand, if you will. There are rocks that we replicate. And we have slopes as well so that we can climb the vehicle on the slopes. In doing that, we typically will find bugs.
Glitches in the software, the rover's brain.
And as we've come up with fixes, we will uplink those fixes to the real vehicle. And that is the purpose of my team, so that hopefully we find these issues before they happen on the real vehicle. In case things go wrong, we better figure out how to fix it through software, because at this point in time, we can't send mechanics to Mars. I'm an avid user of social media, and some of the images I've posted are of myself working on the vehicle. I think personally, being a Hispanic man, it's very important for people like me to understand that there are people that look and sound like me that are working on such technologies. That is why I share what I do. And I like to show people what we're doing because it's pretty unique.
A few months after Perseverance lands on the Red Planet, it will drop a special little package on the surface that could revolutionize the future of space exploration. A tiny copter named Ingenuity could be the first aircraft to fly on another planet.
When we first proposed it, there were a number of naysayers, even at JPL, who said, oh, this thing can never fly.
I felt it was going to be challenging every step of the way. In fact, at the beginning, it was a question of even feasibility. Can it be done?
What makes flying on Mars so challenging is its extremely thin atmosphere, 100 times thinner than Earth's. The thinner the atmosphere, the harder it is for a helicopter to generate lift.
Fundamentally, a helicopter flies, by first generating lift, and the lift is generated by the blades pushing the air, and that provides the lift.
On helicopters, the blades are curved on top and are also angled to redirect the airflow downward. Because of this design, as they rotate, the air pressure on top of the blades decreases, and the air pressure underneath the blades increases. That difference in pressure pushes the helicopter up. Earth's dense, thick atmosphere helps make lift possible. In order to fly on Mars, the team had to find a way to compensate for its thin atmosphere, to rethink the physics of flight.
You have to build a vehicle that has a large blade, significantly large, proportional to the size of the vehicle. And the blades have to spin very fast, and the vehicle has to be very light.
In 2018, the team took their copter on a test run. This special chamber has had most of the air sucked out of it, so it can accurately mimic the thin atmosphere of Mars.
This is a moment of truth. You send the command, the helicopter is sitting on the ground, and it starts spinning, and the danger was, is it gonna start, skittering across the chamber floor? The vehicle was perfect. It was balanced so perfectly. Our minds go back to what the Wright brothers must have gone through. The first moment they took flight, they must have felt the emotion, the feeling, the reward they were looking for.
It's been a long journey. We've done all the testing here on Earth, and now it's time to go to Mars and prove that this thing can really fly in the actual environment of Mars.
If all works as planned, Ingenuity will take a series of flights over about 30 days, venturing farther with each flight.
When astronauts get to Mars, in the future, being able to scout and survey and just having the aerial dimension will be crucial.
To make the whole planet accessible through a new form of mobility is going to be transforming in terms of what it does for exploration.
Another passenger on Perseverance could help turn our sci-fi dreams of human exploration into a reality. In fact, in the feature film The Martian, Mark Watney couldn't have survived without it.
In the movie The Martian, there was a mention of a device called an oxygenator.
Everything here that's keeping me alive, the oxygenator, the water reclaimer.
Which we like to think of as maybe the great-great-grandchild of Moxie.
This little gold box named Moxie will test whether it's possible to take deadly Martian air and create breathable air. The air on Mars is not only thin, it's rich with carbon dioxide, CO2.
So what we're trying to do with MOXIE is to take a carbon dioxide molecule, CO2, 1 carbon, 2 oxygen atoms, and split off one of those oxygen atoms.
An oxygen atom doesn't like to be alone. After it breaks away from the carbon dioxide, it joins with another oxygen atom, creating O2, which is in the air that we breathe. Here on Earth, the atmosphere has plenty of O2, thanks to photosynthesis.
We take all that oxygen for granted. When we're on Mars, we have to make the best of what we've got and get our oxygen out of that carbon dioxide.
Breathable oxygen will be crucial for humans to survive on Mars.
There's no question, if I were going to Mars, I would want oxygen to breathe. But that's not anywhere near the major requirement for oxygen, assuming that I want to leave the surface of Mars, get back to orbit, and catch my ride home to Earth. I'm going to need a lot of propellant in a rocket to get me off the surface of Mars. Tens of tons, in fact. Whether you have a campfire, whether you have an internal combustion engine in a car or a truck, anytime you want to burn something, you need two things. You need a fuel, and you need oxygen.
To take off from the surface of Mars with a crew of 4 in a rocket about the size of this pickup truck, how much fuel and oxygen do you need?
Well, we need about 7 tons of fuel. That's a lot of fuel. And we need about 25 tons of liquid oxygen to burn all that fuel. To picture how much that weighs, we can start with a 5-gallon jug of water, the kind that we put on top of the water coolers. If we wanted to put that much liquid oxygen in those water jugs, we would have over 1,300 of those jugs. So imagine putting 1,320 water bottles in the back of this truck. That would be tens of feet high stack of water bottles. Too much even for the water bottle delivery van, never mind this little pickup. That oxygen turns out to be the single heaviest thing we would need to take on a mission to Mars with astronauts. It dominates the cost and the complexity of the mission. So what if we can start living off the land by saying, we're not going to bring any oxygen with us. We're going to make it on Mars and use the oxygen that we make to fuel the rocket that will take our astronauts home, that will take Mark Watney home.
If MOXIE can efficiently create burnable oxygen, then the sci-fi dream of human exploration of Mars may become a reality.
It's clear that the United States is putting in a big effort to send astronauts to Mars, and the technologies that we are demonstrating are going to make that easier.
Perseverance will test technology that will take exploration into the future as it collects samples of Martian rock. Once it's done, how will these samples make their way back home?
Mars Sample Return really is an international program between NASA and ESA.
We all come from different backgrounds, and we have, of course, different roles to play in the bigger picture, but everybody is working towards the same goal. If you think about it, it's amazing how a collaboration across the globe can come together to do such an amazing thing.
Current plans call for another lander to travel to Mars within a decade, and a multi-part mission to bring the sample tubes back to Earth will begin.
It would be a big risk, a big gamble to bet the whole of Mars Sample Return on the fact that Perseverance would still be alive and fully functional after almost a decade on the surface of Mars.
So researchers across the globe must prepare for different scenarios.
Perseverance rover has the possibility to either hang on to sample tubes or drop them onto the surface.
Just north of London, engineers at Airbus are preparing for one of these scenarios. Meet Fetch. Think of this little rover as a celestial messenger service.
Perseverance will drop the sample tubes on the surface of Mars, drive a little bit away, and take a lot of good photos to document exactly where the sample has landed. And we will be able to direct the sample fetch rover to the general area within a meter or so of the actual samples on the surface.
Once Fetch gets close, it will need to find the sample tubes on its own.
We need to have autonomous systems on board that can take a picture of the scene in front of it, identify what's a rock, identify what's a crack, identify what is the tubes.
Fetch starts by taking a picture of the general area where the tubes should be.
So this is the raw image that we've taken right as we've approached these sample tubes. You can see on the raw image that there's clearly a number of tubes dotted around the terrain, as well as a couple of rocks.
Through a series of steps, it decodes the scene, homing in on the tubes based on their shape and color.
In the times that the tubes are on the surface, there will certainly be some form of dust deposition on them. Sand might build up a drift on one side of the tubes, but it's not going to be a thick coating that completely obscures it.
Fetch comes up with a plan to grab the tubes. But it can't do it without Delion, a savvy robotic arm being developed in Italy. This lightweight arm is equipped with a brain of its own.
This operation must be performed autonomously with the vision system.
In other words, the brain of the rover and the brain of the arm work together to locate and pick up the samples.
Being able to do that is something that's completely new, completely novel. It's not been done on any Mars missions before, so it's something that's a key development challenge that we're working on.
Once it collects the tubes, Fetch will bring them to a pint-sized rocket.
The most challenging element of that whole architecture is going to be launching a rocket off of Mars. That is super ambitious. That will be a first.
The rocket, designed by NASA, will release the samples, which will be grabbed by another orbiter, designed by ESA.
The Earth Return Orbiter is hurtling around the Martian planet by 7,600 miles per hour. The job for an orbiter is to slightly adjust its velocity to make sure that we can capture this basketball inside a hoop. We'll have some sort of trapdoor that opens, and then we'll basically swallow this basketball up and put it into our spacecraft.
Through various stages of mechanisms and airlocks, if you will, put it inside a Earth entry vehicle that itself will be clean, and we will have these various layers that will protect the Earth when we bring that sample back from Mars.
To protect Earth from whatever the samples contain.
Incredible safeguards are being developed to make sure that any object brought from Mars remains in an environment that is completely cut off from Earth environment in every possible instance and manner.
The nice thing about sample return is we've done it in the past with the moon, the Apollo samples. Samples were treated as hazardous until they could prove that it did not affect humans negatively. And the same thing will be done for any sample return mission. The items are treated as potentially hazardous until we know that it's safe. You want to be overly cautious. You want to make sure that you prove without a shadow of a doubt that it is not hazardous to humans.
But long before we would confront any potential danger from Martian samples, Perseverance must land where no rover has dared land before. Back in May 2019, in the heart of Death Valley, a team of engineers test a new autonomous landing system they hope will give their rover the ability to steer out of trouble, to be its own pilot.
we get one chance, we have no opportunity to fix it, and it has to work the very first time.
Inside this trailer is a makeshift mission headquarters where they will monitor if the new landing system actually works.
Our previous missions really only had one computer, one brain that was doing the entire entry, descent, and landing sequence. Now we have two.
Two brains that must work hand in hand to guide the rover to land safely near the delta of Jezero Crater.
That delta has created this cliff that's like 60 to 80 meters tall, kind of along the lines of how tall we're seeing the terrain behind us.
The rover must land close to it, not crash into it. To test the rover's new brains, the team secures one on the nose of a helicopter and the other behind the cockpit. The helicopter and brains take off, heading to a section of Death Valley that looks remarkably like the surface of Mars.
Typically, when we do these tests, you start out very nervous, and often things break and you have to fix them.
We're really trying to find the unknown unknowns. What if we didn't think of something that really will affect the mission?
Hammer, do you read me?
The helicopter goes above 10,000 feet.
Which is pretty high for a helicopter to fly.
High enough for the crew to need oxygen. And around the same height where Perseverance will start to use its pilot's brain to land on Mars.
Just like you and I can take a map and look at it and then look around and see different landmarks and see what's where on the map. The rover figures out where it is based on knowing where all the landmarks are in the map and then identifying them.
A lot like the job Pete Conrad and Alan Bean faced when they landed on the moon on the Apollo 12 mission.
Okay, we're out at 19,000 feet. I got some kind of a horizon out there. I got some craters too, but I don't know where I am yet.
They were looking out the window at different craters and different features on the moon.
I think I see my crater.
That they knew of from maps of the moon.
Hey, there it is. There it is. Oh my God, right down the middle of the road. Outstanding.
They figured out where they were. We're doing the same thing that those astronauts did on Apollo 12, just on Mars.
The vision computer is telling the rover computer, here's where I am, here's where I am, here's where I am. The rover computer takes where we are, figures out where we can go, and picks the safest spot in the place where we can actually reach. And it does all of that in a snap of a finger.
In the trailer, the team tracks the brain's progress.
So on this side, we have a map that we've made of our landing site that we're matching to, and this is the image that's taken on board.
The squares on the monitors represent landmarks. The colors tell them if the brain on the helicopter is correctly identifying those landmarks and matching them to its map.
So green ones are ones that are good, that we matched correctly, that the system believes are correct.
After 6 runs over the desert, there's plenty of green on the map. The rover's brain appears to be up to the task. But will it work on Mars? February 18th, 2021. Almost 2 years after their test run in Death Valley.
Standing by for cruise stage separation.
The team attempts to land their rover in Jezero Crater under circumstances no one could have prepared for. Because the pandemic still rages across the country, many team members watch from the safety of home.
I'm feeling really nervous and excited. The past 5 years of my life has been spent working on this project. I wish someone could hold my hand.
Like everything in life, you get up and there's no guarantee that your day will go well.
3:48 p.m. Eastern Standard Time.
MTFSW on.
Perseverance begins its descent.
We have confirmation of entry interface.
As soon as the spacecraft hits the top of the atmosphere, it's minutes between that moment and landing on the surface of Mars.
Although there are cameras on board, the team can't see any imagery during landing.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration.
Parachute has deployed.
When the parachute's open, that's big, because you slow down a lot with that one.
Even though we're under a huge parachute, we're still descending at about 200 miles an hour. That's actually a little faster than I'd be going if I jumped out of a plane and dove headfirst without a parachute.
Perseverance is now slowed to subsonic speeds, and the heat shield has been separated.
Once the heat shield falls away, our lander vision system is taking pictures of the surface, trying to figure out where it wants to land.
We have 10 seconds to do that. Things happen real fast after that.
The vehicle drops itself into like free fall, turns on the retro rockets.
Skycam maneuver has started.
The rover slowly was tethered down to the surface. It was an incredible, few moments of anticipation.
You want to hear it, you're waiting for it, and then they call it.
Touchdown confirmed. Perseverance safely on the surface of Mars.
Wow.
Still in disbelief, excited. It is incredible. It is incredible.
Oh my gosh.
Seriously.
As I was celebrating, the image comes in.
There's a picture.
I just could not believe it, that Mars was saying hello to Perseverance so quickly.
You want to see the dirt. You want to see the dust on the wheels. It's real. It actually happened. I just want to hug somebody.
Later, actual video of the landing finally comes in.
This is just insanely awesome footage. James Cameron, eat your heart out. Just to see how utterly amazing all of this engineering is and all of the stuff that went into making this happen. The ones and zeros and the forces and accelerations and rates, that doesn't really do justice. That sort of numerical purity doesn't do justice to all of the emotion and humanity that went into making something like this happen.
We're not landing as a city or as a country. We're landing as the blue planet, right? And the blue planet is going to the red planet, and we're going to be exploring it together.